our next goal would be to generalize this expression that we gave for a holomorphic for a function f which has a pole at z0 and get hold of a more general such series expansion which is called the Laurent series expansion. So, in order to do that, we will be now considering functions which are defined on an annulus, and we will be considering doubly infinite series. So, before we really start developing our theory with Laurent series, let us set certain notations that we will be using. So, Laurent series. So, let me first talk about what is meant by a doubly infinite series. So, let Zn, where n is all positive and negative integers, be a doubly infinite sequence. Sequence of complex numbers. Then the expression summation n is equal to minus infinity to infinity Zn, this is an expression, is said to converge if the two sequences summation Zn n is equal to 0 to infinity of the non-negative indices converges and the summation of the terms with negative indices. So, maybe I should put minus n here and n equal to 1 to infinity converges. So, if both these sequences converge, we then say that this doubly infinite series summation n equal to minus infinity to infinity of Zn converges. We say that summation Zn converges absolutely if summation Zn where n goes from 0 to infinity converges absolutely and summation n equal to 1 to infinity of z minus n converges absolutely. If both these series converge, then we say that the doubly infinite series converges absolutely. Yeah, in these cases, we then say that the let me just say then summation, we say that summation n is equal to minus infinity to infinity of Zn is equal to summation n is equal to 0 to infinity of Zn plus summation n is equal to 1 to infinity of Z minus n. This is what we mean by a doubly infinite series. We define uniform convergence also very similarly. Maybe I should just write it down. Let un for n equal to 0 plus or minus 1 plus or minus 2, basically integers, be functions defined on a set capital U. We say that the doubly infinite series converges uniformly on U if this series summation un of z n going from 0 to infinity converges uniformly on U and summation n equal to 1 to infinity of U minus n of z converges uniformly on U. So, we have now really talked about what is meant by absolute convergence of doubly infinite series. We have also talked about what is meant by the uniform convergence of a doubly infinite series. Let me just set up one more notation that is needed for the Laurent series development that I am talking about. We will define an annulus around Z0 to be a disk of radius R2 with a disk of radius, closed disk of radius R1 inside it removed. So, an annulus A Z0 R1 R2 around a point Z0 for R1. Okay, what is R1? For 0 less than or equal to R1 less than R2. By the way, R2 could be infinite if, yeah, so what is this? Is the set, is the open set given by the set of all Z in C such that R1 is less than mod Z minus Z0, which is less than R2. Let me draw a picture to describe what the annulus is going to be. The red is going to be the circle of radius R2 and the violet is going to be the circle of radius R1 around the point Z0. So, we have this is R1 and this is R2. And what is our region A? It's the yellow region that I am going to shade. It's the region which is bounded between these two circles. This is precisely an annulus of radius R1 and R2. So, if R2 is infinite, we will just end up with the set of all Z such that mod Z is greater than R1. That's precisely, that's the complement of the closed disk of radius R1, right? Okay. So, we now have all the ingredients to talk about the Laurent series development around or in an annulus. So, let me just describe the theorem for you first. Laurent series expansion. Maybe I just write Laurent series. So, let us pick some a function f which is holomorphic on one such annulus. So, notice that r could be 0. What will happen if r is equal to 0? If r is equal to 0, that is just going to be the punctured disk of radius r2 with z0 removed, which is going to be of special interest to us because that is precisely where our isolated singularities are, right. That is precisely where that is the domain where we are interested in when we are studying isolated singularities. But anyway, let us first develop the Laurent series development in the more general setting of a more general annulus. So, let f be a function holomorphic on a z0 r1 r2, where a z0 r1 r2 is as above. Then there exists a n in C for n in integers such that f of z is equal to summation n is equal to minus infinity to infinity the doubly infinite series given by a n times z minus z0 to the power n, where on a z0 r1 r2 where the convergence is actually absolute convergence, where the doubly infinite series converges absolutely. So, let me not write this because I am going to also talk about some uniform convergence. This is going to converge absolutely in the annulus a z0 r1 R2 and uniform on a smaller annulus. Uniform in A Z0 small r1 r2 where capital R1 is less than small r1 which is less than small r2 which is less than capital R2. So, if you take any smaller subannulus, in such subannulus this convergence is going to be uniform. Moreover, we do have some knowledge about what an is. Moreover, an is just going to be equal to 1 by 2 pi I integral over gamma f of z by z minus z0 to the power n plus 1 dz, where our gamma of z is just going to be equal to z0 plus r e to the power I t for t in 0 to 2 pi, where r is some number between r1 and r2. So, we not only know that our function f can be written in doubly infinite series. This is called the Laurent series of f around z0. So, let me just write that down, called the Laurent series of f around z0. And we know exactly what each of these coefficients are. See, if you try to find the analog of this with holomorphic functions defined on dz0 r2, say, what would have happened is that we do have a power series expansion, and that's a series which starts from 0 to infinity. Here, however, the disk of radius r1, closed disk of radius r1 is removed from the disk of radius r2, and the series development is in this annulus that we are considering now. So, let us give a proof of the Laurent series development. The first thing to note is that the R here is not special. So, proof. Notice that for R1 where capital R1 is less than small r1 less than small r2 less than capital R2, we have gamma 1 of t given by z0 plus r1 e to the power it for t in 0 to 2 pi, and gamma 2 of t given by z0 plus, maybe this is r1 and this is r2 e to the power it again for 0 to 2 pi. Gamma 1 is homotopic to gamma 2 as closed curves in A Z0 capital R1 capital R2. So, what have we just written down here? Let me draw a picture to capture that. What was the outer radius? Red and violet. So, if you start off with an annulus like this, and if you take any two circles here, so this is our region, right? The region shaded by z0 is what we are interested in. In this region, if you take any two circles centered at z0, say this is r1 and say the orange one is small r2. These are all circles centered at z0. What this tells us is that through the dark green straight line homotopy, these two curves are going to be homotopic to each other. And because of that, any holomorphic function defined in this particular domain will have the same integral over these two curves. So, hence, let me just note that, hence, if you look at f of z by z minus z0 to the power n plus 1, which is holomorphic over gamma 1 is going to be the same as the integral over gamma 2 of f of z by z minus z0 to the power n plus 1 dz. because they are homotopic to each other, and this function f of z by z minus z0 to the power n plus 1, that is a function holomorphic on the annulus where the homotopy is defined. So, there is nothing special about the R which we actually picked, and therefore, we get to know that this Laurent series expansion that we have, that is unique. So, if we know the existence, if we somehow manage to prove the existence of such a Laurent series expansion, we know that it is a unique expansion. Let us now try to prove the existence of such a Laurent series. To do that, let us again draw a few pictures. So, this is the circle of radius R2 around Z0, and we indeed have a circle of radius R1. What we will do is, let us define a function on the disk of radius R2. Let us define a function on this entire disk, which is being shaded by blue here. So, on dz0 R2, let us define a new function. Define g of z to be equal to the integral over a curve gamma. I will describe what gamma is. This is the integral of f of maybe zeta by zeta minus z times d zeta. Maybe zeta is unnecessarily complicating. Let me use w as the variable, w minus z dw. If you look at the curve gamma, where gamma of t is equal to z0 plus r e to the power it. So, let me just put an r in the subscript to capture the r that is featuring here. And what is the property of r? Where absolute value of z minus z0 is less than r, and r is between r1 and r2. So, let us spend a few seconds trying to understand what is happening here. What is our gamma of t? Suppose we take a point somewhere here, and let us call this z. What we are doing is, we are getting hold of gamma subscript r, which is being drawn by using the orange here. So, if our point z was somewhere here, then it did not matter, any r between capital R1 and capital R2 would have worked. But if it was in the annulus, just pick some particular small r which satisfies the condition that mod z minus z0 is greater than, or rather less than, small r, and define g of z to be exactly equal to this integral. Then the first claim is to check that g is a holomorphic function. It is in fact continuous and holomorphic on dz0 comma r, or rather R2. Did I put R2 above? Yes, R2. It is the bigger disk that we are looking at. So, the first check is to see that g is indeed continuous. So, let z z prime be some point in dz0 comma r, and then let us look at what happens when we approach z. So, what is going to be g of z minus g of z prime? Again, let me draw a picture. Suppose this is our z here, z prime here. Take a small neighborhood such that this is contained here, and let R be some circle of this type. All right. Then, what is the first observation? This is just going to be equal to, by the very definition, this is 1 by 2 pi I integral of f of w by w minus z dw minus 1 by 2 pi I integral of f of w by w minus z prime dw. And if you write that down explicitly, this is going to be 1 by 2 pi I integral f of w is going to be common times w minus z prime, which is z prime minus w minus z. So, z minus z prime by w minus z times w minus z prime dw. This is precisely what the integral is going to be. Now notice that the z minus z prime can be taken out. So the absolute value here is going to be the absolute value of this difference, which is the absolute value here, which is equal to the absolute value of z minus z prime times the absolute value of the integral over gamma of f of w by w minus z times w minus z prime dw. Now that is the precise reason why we picked a disk of this type. On this disk, we can say that w minus z and w minus z prime are bounded below. So we can say that on dz prime epsilon, for epsilon small, absolute value of w minus z is greater than some delta, and w minus z prime is also greater than some delta for all w in gamma, in the image of gamma. And therefore, what do we have? We can write this thing inside, and also f is a function which is holomorphic on the annulus, and in particular it is continuous on this circle, and hence being compact there will be a bound. Therefore, we can write this as absolute value of z minus z prime times m by the absolute value of w minus z and w minus z prime, both of which are bounded above by below by delta, and hence 1 by w minus z times 1 by w minus z prime is bounded by delta square, and the arc length of gamma, which is going to be equal to 2 pi r. So if you notice, entire thing in this bracket is a constant, and if you take our epsilon, this epsilon to be small enough, we can make our right hand side as small as we want, and this tells us that G is continuous at Z prime. So before we go ahead, one thing to note here again is that this definition is well defined. I did not spend any time to justify that. I did not say any extra restriction on R, only this was the restriction put on R, but then the function which is circled now, f of w by w minus z, that is a function which is holomorphic on the annulus, which has the lower radius greater than absolute value of z minus z naught and upper radius r2. So there the circles are homotopic to each other, and this particular integral is hence not going to depend on the exact circle that we are picking. So this definition is certainly well defined. I forgot to mention that. Anyway, we have now even established that G is continuous. Now if you look at what is G of Z minus G of Z prime by Z minus Z prime, what is that going to be for Z not equal to Z prime? We have what that number is going to be. That's going to be equal to the 1 by 2 pi I integral over gamma f of w by w minus z times w minus z prime dw. So it's a good exercise to sit down and convince yourself that as z goes to z prime, limit z goes to z prime. The techniques are exactly similar to how we established G is continuous. Just a little more computations and work is needed, however, to establish that this limit as z goes to z prime of the function g of z minus g of z prime by z minus z prime, this is going to be equal to 1 by 2 pi I integral over gamma f of w by w minus z prime square dw. And this way we will be able to conclude that G is holomorphic on dz0 r2. So let's just go back to what we did. what we did was, on this bigger disk dz0 r2, we defined our function g of z to be in this manner, and we just noticed that g is a holomorphic function there. Let us now define one more function h of z. Define h of z on the complement of the closed disk of radius r1 on the set of all z such that mod of z minus z0 is greater than r1. Remember that r1 is the smaller radius in the annulus, and on the region above we are going to define h of z to be equal to h of z is minus of 1 by 2 pi I integral over gamma, maybe I will put an r here, where gamma r is exactly as earlier. It is going to be the circle of radius r around z naught of f of w by w minus z dw. So, this is on this region, remember that the z comes from there. And how about r, where r now is less than mod z minus z naught, and it is between r1 and r2. Yet again, all the arguments that we gave earlier for g of z goes through for h as well. H is a function which is holomorphic on the region z such that mod z minus z0 is greater than r1, and we also have that it is well defined, it does not depend on the exact r, because f of z, w by w minus z will be holomorphic in the relevant annulus that we will be considering. So, let me not go into the details again, it is just a repetition of the arguments which we gave for our function g. Okay, now we have two functions, one defined in the disk of radius capital R2 and the one which is defined in the complement of the disk of radius closed disk of radius small capital R1, which is less than R1 is less than R2. So, what have we done? Let me just draw a picture and tell you what was done. So, this is the disk of radius R2. What was done was that in the red region the function g is defined, and by considering the purple circle which is the radius of capital R1, outside this disk we have defined our function h. So, notice what has happened on the annulus, both g and h are defined. So, let me now draw one more picture to capture what happens inside the disk of the inside the annulus of radius r1 and r2. So, let me draw the annulus yet again for you. This is our annulus, and r1 and r2 be the radii. This is our point z0, and let us now consider an r1 which will be captured by say green, which is a circle of radius small r1, and the pink will capture the circle of radius small r2, and such that we have our point z somewhere here. So, let us see, let z be a point in a z0 capital R1 capital R2 and small r1 less than small r2 be such that r1 is less than mod z minus z0, which is less than r2. Now, let us take a curve gamma which is maybe taken by orange and joining gamma r1 and gamma r2. So, let me just write down the notations. This is gamma r1, this is gamma r2, the outer one is gamma r2 with capital R, and the inner one is gamma r1 with the capital R. That is precisely what our circles here are, and that's the picture that we are capturing as well. Let us now consider the curve, consider a curve. What have I called it? Gamma, right? So let's call it something. Let's call this curve gamma. From gamma 0, gamma r1 0. So this is gamma r1 0 and this is gamma r2 0 to gamma r2 0, such that z does not belong to gamma. Let's call this curve again. Too many gammas, maybe I should change it to something else, or maybe not. Consider a curve gamma. So remember what the curve is. This is our curve gamma. That's connecting gamma small r1 of 0 to gamma small r2 of 0. And then consider the following concatenation of curves. Let sigma be equal to gamma 2, which goes in this direction from here. It comes back to this point, and then you go along minus gamma. So we are going to add minus gamma here, and then we will go along gamma r1 in this direction, which is minus gamma r1, minus gamma r1, and then you come back along, oh this was not minus gamma 2, minus gamma, sorry, and then you come back along gamma. So what is happening? This is the curve which I will draw using yellow, which I will erase after I draw. We go along this curve, go along gamma, go along green, and come back along gamma. So you start off at this point and you reach back. So this is a closed curve. Sigma, then sigma is a closed curve in A, Z0, R1, R2. I am going to say that sigma is also null homotopic. Let me not give you an explicit homotopy here, let me just give you the idea. The idea is that you can go along this curve, go along this curve, this is the starting point, and then at every stage you go like this, go along this curve, and then come back in this curve. And by stage 1 you go along this curve and then come back along this curve. So we are going to be homotopic, this curve is going to be homotopic to gamma 2 plus the reversal of gamma 2, which is null homotopic. So let me just say that sigma is null homotopic in A, Z0, R1, R2, and therefore we can use the general Cauchy's integral formula to conclude that W sigma of Z times f of Z, this is going to be equal to the integral over sigma of f of Z by maybe f of W by W minus Z dW. But what is the right hand side? The integral over gamma 1 f of W by W minus Z dW plus the integral over minus of gamma f of W by W minus Z dW plus integral over minus of gamma 2 f of W by W minus Z dW plus integral over gamma of f of W by w minus z dw. This will cancel off with this being the inverse, and the first one is basically gamma 1, or rather gamma r1, I should be more precise. Yeah, so when I wrote gamma 1, it's just gamma r1, and gamma 2 is just gamma r2. So yeah, maybe it's not correct that I have written what I have written. This is gamma 2 and this is minus of gamma 1. Let me see. Correct, gamma 2, and so at some stage I started messing up with the index. So let me be a little careful, so that you don't have any confusion. So this is not going to be gamma 1. This is gamma r. This is not gamma 2. This is gamma r2. This is gamma r1. Right, and if you go up, this is precisely our g of z plus h of z. I will leave you to check that this is exactly equal to g of z plus h of z on a z0 r1 r2. Recall that both g and h are indeed defined on the annulus. So this is precisely what we have. And we already know that g of z can be written directly as a power series expansion in dz0 r2, capital R2. Now let's see what happens to h of z. Recall that h of z is defined to be minus of 1 by 2 pi I integral over gamma r1 of f of w by w minus z dw, where r1 is such that mod z minus z naught is greater than r1 and r1 is between capital R1 and capital R2. So that's precisely what our h was. So this is defined on set of all z such that mod z minus z0 is greater than r1. Let's now define a new function. Define maybe h1 of z where on d0 less than 1 by r1, and that's, or maybe on the punctured disk around r1. And what is the function that we will be defining? This is going to be equal to h of z0 plus 1 by z. So if you notice, absolute value of z0 plus 1 by z minus z0, this is going to be equal to absolute value of 1 by z, which is greater than r. So it's well defined. H of z0 plus is greater than 1 by r1. That's because mod z is less than r1, 1 by mod z is going to be greater than r1. So this is exactly the place where our function h is defined. So this makes perfect sense. And notice that h has now an isolated singularity at the point 0 at origin. And what happens to this isolated singularity? So my claim now is that our function h1 is a removable singularity, or rather h1 is, by the classification, it's going to be locally bounded around 0. To check this, let's consider what our h of z was. H of z is basically minus of 1 by 2 pi I, the integral over gamma r. So I'll see what r is. We'll fix what r is in a moment. F of w by w minus z dw. R is nothing but a number which is less than mod z minus z0 and between capital R1 and R2. In particular, R1 would have sufficed, and let me just put R1 here. And if you look at the absolute value here, this is going to be the absolute value here. Let's fix the R1, and on R1 we will have mod f to be bounded by some number, and let rho of z be the distance of our point z to gamma r1. That means that the absolute value of mod z minus z, mod w minus z is going to be greater than rho of z. Remember that this is a function which depends only on z. So maybe let me go back up to the image and show you what is happening, or maybe I'll draw a new picture. what is happening is the following. We have our R2 here, there is a small R1 here, and our point Z is somewhere. It could be outside the disk of radius R2 as well, but nevertheless, we will then capture by yellow gamma R1, and rho of Z is the infimum of the distance of Z to any point on the circle of radius r1 and around z0. So that's precisely what is being captured by rho. Because it's the infimum, the distance of z to w, where w is on the disk, is going to be bounded below by rho of z. So hence, what do we have? This tells us that this is going to be less than or equal to m times the arc length of gamma r1, which is 2 pi r1 by 2 pi times dz gamma r1. Notice that gamma r1 is a fixed circle. So the 2 pi is cancelled out. This is just m r1 by dz gamma r1. And therefore, when mod z is made large, we can arrange for dz gamma r2 to be as small as we want. So let me just get back to our h1. Our idea was to show that h1 is locally bounded. So h1 of z, what was h1 of z? h1 of z was h of z0 plus 1 by z, h of z0 plus 1 by z. When z, absolute value of z, is less than say epsilon, mod z0 plus 1 by z can be arranged to be greater than some large s. So maybe I should say that this is less than 1 for mod z less than, or rather greater than some s. This can always be arranged. So suppose this is greater than s, what is happening is absolute value of h1 of z, this is going to be equal to the absolute value of h0 of z plus 1 by z, which is being arranged to be less than or equal to 1. And that tells us that h1 has, because it is locally bounded, has a removable singularity. At 0. That means that h1 of z can be written as summation b n z to the power n, where n goes from 0 to infinity. In fact, notice that here, as z goes to, as absolute value of z goes to infinity, d of z comma gamma r2, this is going to be smaller and smaller. This goes to 0, or rather this goes to infinity, and therefore 1 by this goes to 0, and therefore h is going to, the absolute value of h is going to converge to 0 as the absolute value of z goes to infinity. So that effectively tells us that the absolute value of h1 of z goes to 0 as z goes to 0 in this particular case. So what do we have? We have in fact ensured that since h1 of 0 is going to be equal to 0, this is force, it is a removable singularity, and the limit is going to be 0. We have b0 is 0, h1 of z hence is going to be equal to summation n is equal to 1 to infinity bn z to the power n. This is precisely what our power series expansion of h1 around 0 is going to be. Recall that h of z is defined, h1 of z is defined as h of z plus z0 plus 1 by z, and hence h of w can be written, or h of z can be written as, so if z0 plus 1 by z is equal to w, then we have z is equal to 1 by w minus z0, and that is going to be equal to h1 of 1 by w minus z0, right. So in particular, if mod z is, if z is in the set of all those points such that mod z minus z naught is greater than r1. In particular, if you look at h of z, that's going to be equal to h1 of 1 by z minus z naught, which is perfectly in the valid domain of definition of h1. Notice that 1 by mod z minus z naught is going to be less than 1 by r1, and that's precisely where our h1 is defined to be, right? And this is going to be equal to, by the very definition, bn times 1 by z minus z0 to the power n, where n goes from 1 to infinity. By calling bn to be minus n, we have this is going to be equal to summation a n z minus z0 to the power n, where n is from minus 1 to minus infinity. And therefore, f of z, which is equal to g of z plus h of z, we can write this as summation a n z minus z0 to the power n, where n goes from 0 to infinity, plus summation n from minus 1 to minus infinity of, or maybe 1 to infinity of a minus n z minus z0 to the power minus n. Combining it, we can write this as the Laurent series expansion that we were intending to write it as. This is minus infinity to infinity of a n times z minus z0 to the power n. And with that, we complete the proof. So let's go back. It was a long proof. Let's go back and check what we have proved. What we have effectively established is that when f is a function which is defined and is holomorphic in an annulus of r1, r2 radii, then we can write the function f as the Laurent series expansion given by summation a n z minus z0 to the power n, where the indices are now from n equal to minus infinity to infinity. And we noticed that when r1 is equal to 0, what we effectively have is a power series, Laurent series expansion of a function which has a singularity at the point z0. So let's return to the singularity problem. Suppose f has a singularity, isolated singularity. At z0. What would that mean? This means that f of z is equal to summation a n z minus z0 to the power n from minus infinity to infinity on dz0 r minus the point z0. So notice that the lower radii here r1 is equal to 0 and the r2 is our capital R. And in that annulus, which is the punctured disk, our function f can be written in this Laurent series expansion. Suppose the function f has a removable singularity. F has a removable singularity. What does that mean? That means that you can write f as equal to g on dz0r minus z0, where g is a function holomorphic on dz0r. And by using the power series expansion there, f of z is going to be equal to summation a n z minus, maybe a n, let me not use a n, b n z minus z0 to the power n, where n is equal to 0 to infinity. And that tells us that a minus n in the Laurent series expansion, this is on dz0r. So in particular, it's in dz0r minus z0 as well. And by the uniqueness, we have a minus n is equal to 0 for all n less than 0. And if you backtrack, if a minus n is not going to be the case, a n is equal to 0 and n is less than 0. And if you backtrack, maybe I shouldn't write it down, if you just go back along the same things, and if you assume that for all n less than 0, a n is equal to 0, then f will be having a power series expansion, and that can be thought of as a function on dz0r rather than on dz0r minus z0, and therefore z0 will turn out to be a removable singularity. So, maybe a proposition would be to conclude that f has a removable singularity at z0 if and only if an is equal to 0 for all n less than 0 in the Laurent series expansion of f. Laurent series expansion of f around z0. This is an if and only if statement. Now let us see what happens when f has a pole. If f has a pole at z0, then as was noted earlier, z minus z0 times to the power m times of order m, let us put it this way. Then z minus z0 to the power m times f has a removable singularity at z0, and we will be able to conclude then that f of z, in fact we already have written f to be equal to am by z minus z0 to the power m plus all the way up to a1 by z minus z0 plus summation, maybe I should call these bm's, an z minus z0 to the power n is equal to 0 to infinity. And because of the again uniqueness of bm's, this is on d z0 r minus z0, and this tells us that am is equal to, or rather an is equal to 0 for all n less than m in the Laurent series expansion. Around z0 of f. And if you backtrack these arguments by going along the opposite direction, you will see that if an is equal to 0 for n less than m, then our function f has a pole of order m. So, let me just write that down as a proposition as well. F has a pole of order m at z0, where m is some positive number if and only if. So, maybe I should be a little careful when I wrote this here. So, I hope I have made the right choice. So, this is going to be minus m actually, because there were m terms to the which had the negative power, right. Even though I wrote this, maybe I should have been a little careful. I will just write this as d minus m minus 1, so that the fact that negative powers are being considered is captured. So, let me just put it this way. And here we are just saying that the same thing we are saying, an is equal to 0 for n less than minus m in the Laurent series expansion. Again, this is an if and only if statement. Of f around or in d z0r minus z0 in the annulus. So, remember that this is the annulus. I have constantly used this. This is the annulus of radii 0 and capital R, and there is the Laurent series that we are considering. And finally, if neither of this happens, that is going to be an essential singularity. F has an essential singularity at z0 if an is equal to 0 for infinitely many negative indices, or rather if and only if an is not equal to 0 for infinitely many negative integers n. The Laurent series expansion hence gives us a lot of information about the isolated singularities of our given function f. In fact, we have characterized all our isolated singularities by studying how the Laurent series behaves in the punctured disk of radius r around z naught.